Welcome back. Let's finish homework 11.3. I think I left off with number 20, so I'm going to pick back up with number 21. This is a few days later. So we've got a series that we're going to approximate with 13 terms. Okay, so I'm going to copy the series. N minus 3 squared. I think that meant to be an n plus 3 squared, right? Because where n equaled 3, that was going to be infinite, and that would not be a convergent series. We couldn't add it up. The total would not be defined because one of the terms wasn't defined. Okay, it's going to be n plus 3 squared. And we know this is going to converge because it's an alternating series that grows faster on bottom. So its terms are going to be decreasing. The limit of them is going to be 0. We know it's going to converge. Okay, if we approximated it with 13 terms, the alternating series error bound, which is kind of like if the total sum is s when I add up all infinity terms, we can call it s infinity. The alternating series error bound is the absolute value of the difference between s infinity and s13. But we know that that error is no more than the absolute value of the 14th term. Okay, so I'm just going to say A14. We're going to come back on this in a little bit. I saw that there was a question down there that was, I think it was related to a multiple choice question, but it's going to say like true or false, or sometimes always or never, or whatever, and we'll talk about that, but it's writing the alternating series outbound like that. I know the absolute value of A14, right? I can just plug in 14 for n and take the absolute value of it. So the alternating series error bound would be negative 1 to the 14 minus 1 is 13 divided by 13, or for pardon me, 14 plus 3 squared is 17 squared. Okay, and so the error bound would be 1 over 17 squared, whatever that number is. It sounds like it's pretty small though. Okay, 22. The series below converges to S. I'm going to copy that right now. S equals the sum from 1 to infinity of cosine of pi n divided by square root of n. All right. What is the least number of terms in the series that must be summed to guarantee a partial sum for which sk minus s is absolute value, so the error is less than 0.02? Okay, so what we need to do is we need to find the first term that goes underneath that, and then that will be the next term, and we'll go one previous from that. Okay, so I really need to figure out when is, okay, I know in general the difference between the partial sum after k terms and the total sum is no more than the k plus first term, or at least the absolute value of the k plus first term. Okay, and we want that to be less than 0.02. Okay, and all right, well, let's just kind of get to it. The absolute value of the k plus first term is going to get rid of that cosine of pi n because that's always either plus 1 or minus 1, and well, the absolute value of that is just 1. So it's 1 over square root n equals 0.02, which I might also write as 1 over 50. So it's like, when is the square root of n equal to 50? Okay. And then that would be n equals 50 times 50 is going to be 2,500. Okay. Now let's go with the 2,498. You know, maybe we were off by 1. Maybe I just wasn't thinking about this right. Okay, so if k equals 2,498, then the error bound would be less than or equal to whatever I get when I plug in 2,499 into the formula for the terms. Okay, so cosine of 2,499 pi is going to be negative 1, but I'm going to take the absolute value of it, so it's going to become positive. The square root of 2,499. I feel like that's still going to be bigger than 0.02. Looking for a calculator. Maybe you just know, maybe you know, because square root's an increasing function, that's not going to be, you know, big enough. All right, and then 1 over the square root of 2,499 is going to be 0.0200, whatever. Okay. And So if I took 2,499 terms, then the error bound would be equal to 0.02, and so I guess I would need to take all 2,500 terms for the 2,501st term to be less. Okay, so I'm going to need to take 2,500 terms, because if I took just 2,499 terms, the error bound would be 1 over the square root of 2,500, which is exactly 0.02, and they said less than 0.02. Okay, I think that for the most part, the multiple choice questions give you a threshold here that is not exactly equal to the absolute value of the next term, and that it would be somewhere in between two terms, so that it would be more obvious which one we needed to take. Okay, I'll just that's equal to 0.02, so I'm saying k equals 2,500, so that the error bound was that. Okay, that's all I got to say about number 22. Number 23, the series, this is an alternating series, I'm just going to copy it. The sum from 1 to infinity of k equals 1 to infinity, negative 1 to the k plus 1, a sub k, converges to s. And 0 is less than a, k plus 1 is less than a, k for all k. Maybe for all k greater than or equal to 1. Okay. Let Sn be the nth partial sum of the series. Determine whether, okay, so Sn equals the sum from k equals 1 to n of this. And that's Sn is partial sum. Okay, I think that we've got A through F, and I think I mean, it says true or false, give a brief explanation. I think I'm going to go with sometimes, always, or never, because there's a related quiz question on the online quiz for this one that's pretty similar. So I've already got one of the pads up. The first one is that the limit of Sn equals 0. Okay, I'd say that's probably not going to be true in general. In fact, this one must be false because of this. Okay, because the terms are all positive, even still. Yeah, the absolute value of the terms are all positive, but I feel like it could alternate in such a way that it would converge to 0. I think especially, you know how conditionally convergent series are, you can make them converge to just about anything you want. So I'm going to say this is sometimes, specifically when S is equal to 0, right? When it converges to 0, that would be true. Okay, because the limit of Sn is the value that the series converges to. That's what it means to converge, is that the limit of the partial sums exists. Statement B was the limit as n approaches infinity of Sn equals S. This is always true. This is the definition of convergence. So I was just saying. Okay, so I'm going to say always true. That's just what converges means. Okay, that the limit of the partial sums, S, which is the value it converges to. All right. C, limit as n approaches infinity of An equals 0. Yes, this is always true, because this is a convergent series. This is kind of the reverse of the divergence test, but if the series converges, then the limit of its terms has to be equal to 0. Okay. That was C. Okay. D is that the limit of An is equal to S. And I would say this is never true, but I did have somebody bring the problem to me from the online quiz where this was asking sometimes, always, or never, saying, well, what if the terms went to 0 because it was converging and the total series converged to 0? That would be a case where the limit of an happened to be equal to s, but that's a coincidence if s is 0. So I'm going to say almost never, only if s equals 0, because what we were just saying, we know that the limit of an has to be 0. So if s happened to be also 0, then I guess that could be true, but that seems pretty unlikely. E. The absolute value of the difference between s and s10 is less than or equal to a16. Okay, I don't think that this is true. Okay, I think this is probably false. This is, again, almost never true. I can think of one that would be, well, no, because, okay, this is never true, because the terms are decreasing, but they are continuing to be positive. This is not greater than or not less than or equal to. If this was less than or equal to, I could say, oh, what about the series that it's, alternating for a while? Then after a certain point, it's just all zeros. Then I could have that, right? If 10 was the last non-zero term and a16 was 0, and, well, the total is whatever I get after adding up 10 terms because the rest of the terms were 0, then that would be true, but I know that's not going to happen because none of the terms are 0. Okay, so this is never true. I'll give you a bit more explanation on why. Okay. The alternating series error bound tells us that the absolute value of the difference between s and s10 is no more than a11. Okay. But I also know that a16 is less than a15, which is going to definitely be less than a11. Okay. Or at least, probably need to throw some absolute values around this. Okay, since a16 is less than a11, I don't know, is it s minus s10 could still be less than, but it's probably not. Because of the fact that the terms are getting smaller and smaller. If I was to draw one of those kind of rainbow diagrams for you, okay, so suppose we've got S1, S2, S3, 4, 5, 6, 7, 8, 9, 10. Okay, well the maximum possible distance would be A11, but A16 could be really small, and less than the distance that I needed to get to my convergent value. Okay, so I'm going to say this is never true. And then F is the absolute value of the difference between S and S15 is less than or equal to A16. That's true always, because that's the alternating, right? Okay, that's how we set that up. All right, and that's all for homework 11.3. I'm going to come back and record solutions to that online quiz, so you can look for that if you need more alternating series examples. But thanks for watching. That's all.